Okay. So what is carboxylic acid formula or general, like what is there in carboxylic acid?
It has a COOH.
Double OH.
Right. You have alkyl group and COH. Now, if we were to convert this into alkanes, because we're looking at preparation of alkanes, what modification do you have to do?
We have to add hydrogen
And remove the
and remove the
alcohol and
oxygen.
oxygen group.
Okay, there you go. Like not just add hydrogen, but also try and get rid of the oxygen that is attached to carbon, right? And Ritu, so whenever you come across carboxylic acid group, right? So this is the structure of carboxylic acid. So don't consider it separately as oxygen plus alcohol. Like this whole thing is like one set group. That's why it's its own functional group, not like we don't treat it as a derivative or something. And another reason is that, okay, like one small thing about carboxylic acids, because we haven't touched on that in any of the, like we haven't studied about this before. So the reason why carboxylic acid, like this particular group, has an acidic character is because this hydrogen can be let go of quite easily. And the reason for that is there is a resonance in this part of carboxylic acid. So this is what the resonating structures look like. So this oxygen, 2 electrons are here forming a double bond. So remaining you have 2 lone pairs, and this oxygen has 2 lone pairs, right? So what happens is, whether it's carboxylic acid or let's consider the carboxylate ion itself. O minus. So there's 2 lone pairs here, and if oxygen takes hold of this bond pair of electrons also, this ends up having 3 lone pairs. So oxygen being electronegative pulls on the pi electrons here, and because this carbon is losing electrons, it pulls on one of the lone pairs over here. So this is the resonance that is established in any carboxylic acid, like carboxylate ion in general. Clear? So because of this resonating structure, and this resonating structure can be established if there was like an extra pair of electrons that can form a double bond over here. And for that reason, oxygen is able to let go of this hydrogen easily, so that, you know, the electrons are delocalized and there's a resonance formed between this. Okay. So when we're looking at a preparation of alkanes from carboxylic acids, it is easy to get rid of this whole group as a whole, as opposed to trying to add hydrogens or, you know, like removing each of these oxygens. Like this whole thing forms a tight unit because of this resonance. So it's just easy to, you know, just break the bond over here, let go of this whole thing as it is, and add a hydrogen over here. Okay. So we look at 2 reactions when it comes to preparation method of alkanes from carboxylic acids. Both of them deal with removal of carbon dioxide, I think. Yeah, in both cases, it deals with the whole, like you will get 1 carbon less because it's the removal of this whole group. Okay. So let's look at what they are. But were you guys able to follow how and where the resonance is in carboxylic acids?
Ma'am, could you explain the resonance again?
Kaveri, like when you're trying to understand resonance, it's just trying to understand how the electrons are delocalized. Okay. So that you just follow where all the electrons are traveling. So oxygen lets go of this particular hydrogen. So you get COO minus. So this oxygen being electronegative pulls on these electrons from the double bond. And the carbon, again, valency should be fulfilled, right? It wants to be neutral. So it pulls on the extra electrons that this oxygen has. So what you end up, like the other structure ends up looking like this. So you have the negative charge on this oxygen because it's got extra electrons. And there is a double bond formed because the carbon ends up trying to share these electrons. And the same thing keeps going on. Overall result is the same. You still have COO minus only, which is the carboxylate ion. And yeah, so the double bonded electrons keep traveling here and here this way. So essentially it's like this, R, C, O, O, and this, both of these have like a partial double bond. It's kind of like this. There's a negative charge. Okay. So when you're taking down the notes also, like try to make sense of it in your head while you're taking it down. Don't just blindly copy. Okay. So draw the structure, then make sense, where are these electrons going, how it's going, that way.
How did that become like a partial double bond, like the last part?
Because this keeps traveling, right? So in one structure, it has a double bond, the other structure, it became a single bond. In one structure,
Right.
this is a double bond, single bond, and the other structure, it's a single bond. And
So
keep
hence partial. Yeah.
between those. Okay.
And ma'am, what happened to the hydrogen?
So hydrogen, like it's being let go of as H plus. So proton, like that's why we call it an acid, right? Like property of acids is that they can release H plus easily, proton donors. And it's because of this resonance that carboxylic acids are able to have their acidic property. So the resonance is stabilizing the carboxylate ion. So it can, it's still stable even without the H plus. In solution, it can stay as two different ions, even though it's an organic compound and must be covalent. Because of this resonance, it's able to stay nicely as well.
Is this an example of a reaction or like a separate subtop?
It's a separate thing. I'm talking about resonance. And see, we are looking at preparation method from carboxylic acid. So I'm just explaining what happens in carboxylic acid. There is this resonance going on there. That's why it's difficult to break these bonds between carbon and oxygen. So the best way that, how do you convert carboxylic acid to alkanes is to break it right here. Like break it right here and get rid of this whole CO2 part. So that's what the preparation methods usually follow. So that's why the first preparation method is called decarboxylation. Or simpler terms made, it's basically removal of CO2. Like you remove this whole CO2. You don't try to switch this out for hydrogens. You remove this whole CO2 part itself. The reason why we are removing this whole part instead of, see, when we had haloalkanes, right? We just switched out only the Cl part. but we're not doing that over here is because of this resonance, these bonds are much stronger. So it's easier to break this particular bond. Okay, so let me know when you guys have noted this down, then I'll go forward. I'll talk about decarboxylation, like the actual reaction. Okay, 3 of you are done. Arnav, Smira, Adit. So Ritu, Kaveri, Sanat, Rishit. Once you're also done. Okay, cool. So decarboxylation, right? This is the general reaction. So you take a sodium salt of any carboxylic acid and you heat it with soda lime. On heating, what you end up with is an alkane and a carbonate. So the CO2 part is removed in the form of a carbonate. Okay. So we'll take an example like carboxylic acid, acetic acid, CH3, COO. Instead of a direct acid, we're taking sodium salt of it. So COO, Na. So this is the negative ion, this is the positive ion. And soda lime is basically a mixture of. Have you guys come across soda lime before? What do you mean by soda lime? No? So soda is
Is it that thing we use for whitewashing?
close. No. That is quick lime. That's only quick lime or slate lime. Yeah. Soda lime is a mixture, like the soda part of it refers to a sodium compound. In this case, it's NaOH. And the lime part of it refers to your quick lime. So you mix NaOH with calcium oxide, you heat them all together. You end up getting an alkane. Now, because we are removing CO2, what alkane will you get here? Will you get methane or ethane?
Methane.
And
I just heard thane from some of you guys, like methane, like 1 or 2 carbon.
Methane. One carbon.
one.
Methane, CH4. So that's what the whole deal is about. We are decarboxylating this. We are removing the whole CO2 part of it. So only this will get converted to alkane. So you get CH4, and in this case, since we are heating with this, we get Na2CO2, sodium carbonate. Okay. So, okay, any questions about this reaction? No?
So what is the compound called, like the CH3CO? Like, is it like?
You tell me. Sodium salt of carboxylic acid. What acid is this? Like from which acid did you get CH3CO minus?
Carboxylic?
Carboxylate is in general anything that has COO minus. Now यहाँ पे एक CH3 है ना, तो इसका what would be the name for this? Like you guys learned nomenclature, man, right now. Methanoic acid, ethanoic acid, propanoic acid. वैसे किस acid का salt है? Array, you guys forgot all about acids, bases, salts, huh?
Ethanoic acid.
Is it an ethanoid rather? I think.
There you go. So you get this from ethanoic acid, but because this is an ion, this is ethanoate.
So it's sodium ethanoid. Okay.
Correct. Cation is sodium, this is sodium.
Ma'am, I have another doubt.
Hmm?
Like, why did you separate like the soda lime part? Like, why is like one a reactant and the second one's a reagent?
Good question. That's what is the next part. So if you guys have noted down the reaction, I'll give you the reason for why we use soda lime. Yeah, Kaveri?
Not disconnected. Could you please explain this again? Decarboxylation.
When did you get disconnected, Kaveri?
When you wrote soda lime.
Okay, so this is a general reaction. Okay, so you take a sodium salt of carboxylic acid. Carboxylic acid is a functional group, RCOH. This is carboxylic acid. Instead of taking the acid directly, you're taking the sodium salt of that acid. Then you heat it with soda lime. Then you end up getting alkane plus a carbonate. Okay, so for example, sodium salt of ethanoic acid, your acetic acid, formula hoga, this is sodium ethanoate, CH3COO minus Na plus. Heat it with soda lime. Now, soda lime is basically a mixture of soda, basically sodium ka compound, in this case it's sodium hydroxide, soda ash, right, like the base with sodium, soda. Lime refers to calcium oxide. So it's a mixture of sodium hydroxide, calcium oxide. Heat them all together. Then you end up getting alkane and carbonate. So the main thing to note in this reaction is, if you take sodium ethanoate, a 2-carbon acid, you always get the alkane with one less carbon atom. So the reason is that this is decarboxylate. So we're literally removing the COO part of it. So that's why remaining alkane hydrocarbon that will be left out is from the alkyl group that precedes it. So the CH3 turns into CH4 and the COO-Na, like the whole, this carboxylic part of it, turns into carbon. We're heating it with sodium hydroxide, so you end up getting sodium carbonate. Okay, so this is the reaction.
Got it.
Ma'am, I had a small doubt. So as we are removing CO2, shouldn't oxygen also be removed? So are we not doing that? Sorry?
Carbonate mein aa gaya na. So carbonate is literally C double bond O, and I mean, like you have another like single bond O, single bond O. This is literally carbonate ion. And yeah, like the negative charge keeps shifting between these oxygen atoms, resonance with it. So this part of it, you get it from the CO, like the acid, and NaOH ka, basically the other oxygen, you get it from the soda lime. It's a little like there's a mechanism, there would be mechanism behind it. It's a little complicated, which is why we are not going to get into that right now. For now, you just need to know this reaction, that if you heat acid with soda lime, you end up getting an alkane, 0.1. 0.2, the alkane that you get will have one less carbon atom than the acid. Okay, so these are the two important points you need to take from this equation. Now, why are we not just heating it with the base? Why is COO necessary? So the importance of like lime there, like why is CaO like why are we heating it with soda lime and not just like heating it with the base? Because if you look at the end product, calcium has nothing to do with it. You're getting your sodium carbonate, you're getting your alkane, which is basically getting it directly from this only. So why CaO? Point number one, This is pretty important. So CaO absorbs moisture. So it basically keeps it dry. Okay, because if you end up having water, this is going to ionize, this also is going to ionize, and you won't have this reaction taking place. That creates a completely normal, like a basic solution only. So the one reason CaO is required is that it keeps things dry so that you don't end up getting a solution of this thing. Specifically, it keeps NaOH dry so that doesn't end up ionizing as Na plus and OH minus. And another reason why CaO is necessary is it allows high temperature for the reaction. Heat is also quite important, that we are indicating it as a reaction condition. So this reaction takes place at pretty high temperatures. So CaO, usually CaO ka use, like if you look at it in industries, especially in extraction of metals and all, you use CaO as a lining to the reaction vessels and all, so that even if you heat the reaction vessel at pretty high temperatures, it's not gonna break down. So here also it plays a similar role where it allows high temperatures for the reaction. So it absorbs a lot of heat, it protects the vessel. Like, these are the two important roles why we use soda lime. Lime part of it is necessary. So the importance, like without CaO, it's going to be very difficult for the reaction to take place. The reason is that, so even though CaO itself is not getting into the reaction, it allows the reaction to take place. How? By keeping the reaction conditions dry, so that there's no ionization or any tangent that we're getting into. And two, it allows the high temperature so that the reaction can take place. Okay. So once you noted this down, I'll give you guys another reaction, predict the products for that, okay? Or I'll give it the other way around. What acid should be taken, or what is the raw material that should be taken, so that when you heat it with soda lime, you get ethane, that is C2H6. And of course, you're going to have your carbonate byproduct. But I want, like, tell me what acid or what acid ka salt, what carboxylate should I take so that I get ethane as my product to manufacture ethane. So note down the importance of CaO, like that is quite necessary. You might get it as assertion reason, or in general, like MCQ mein hota hai na, role of whatever. This is quite important. So once you note this down, give me the answer to this. What carboxylate should I take in order to get ethane when I heat it with soda lime?
I'm sorry, I sent it to everyone by mistake.
Okay, I won't comment on it. I'll wait for everyone's answer and then.
Carboxylic is basically just carbon and the oxygen, right?
No, So yeah, carboxyl is COO. Carboxylic acid means COOH. So if I talk about carboxylate, again, this 8 aa gaya na, which means it's an anion formed from this. Okay. Okay. Ritu, Smira, and Adit have sent their answers. Guys, quickly, we have a lot more to do. Sanat also sent, okay? Right, so Rishit, Kaveri, Rishit also sent. Cool. So Kaveri and Arnav. No idea. So Kaveri, you've written the previous reaction, no? So look at the pattern and then based on that, build it up. Arnav, you need to check your answer again. That is not correct. Rest of everybody who has answered correctly. So Kaveri, like, do you have any sort of an idea? Like, give it a try. What logic are you applying? Arnav, give it a go again. Kaveri, but C2H5 is incomplete. Na? Give me the proper compound ka name. You got it right. Build it up from there. C2H6 matlab you need to have C2H5 and the raw material that we're using is carboxylic acid ka salt. So COONA. There you go. Now you guys got it. Yeah. Simple. That's how you figure it out. So carboxylic acid to alkane matlab ignore the COO part because that part is always going to escape. Like that part is the one that's going to be removed. So whatever R group you have beyond COO, that's what is going to turn into your alkane. So this part is going to give the alkane. So if you have a question the other way around, like I asked right now, ethane hai na, C2H6 hai matlab the R part should have 2 carbons, so say C2H5 and the rest of it you can just build it. So soda lime matlab carboxylate acid. So associate the same pattern that I told you guys last class. Always go with substrate, reagent, and product. Okay, so these three are a set. Always learn the reactions as sets of ये substrate के साथ ये reagent है मतलब ये product form होगा.
Ma'am,
Yeah, Sanat.
so we don't have to put the minus and plus signs on O and NA.
It's fine. Like again, that's not exactly convention. This also communicates acha ye product hai. And the reason why some places you put the minus plus is because normal salt mein hamesha cation pehle aata hai na. But because this is an organic compound, that convention just like you write as per the structure of organic compounds. So
Okay.
that's why sometimes you find this, sometimes you don't. So it's fine either way. Okay, so this is one method. One method of decarboxylation is by heating with soda lime. The next method of decarboxylation is, this is a named reaction, so you know it's going to be important. Kolbe or Kolbe's electrolysis. Or electrolytic method. I think that's how it's given in the textbook. Okay. So the hint is there in the name itself. Electrolytic aa gaya matlab you're going to use electrolysis. Okay. So isme we'll be discussing the mechanism as well. But before we get into it, I'll give you guys what is the basic reaction, like what is the pattern. इसमें भी because electrolysis hai, you need to start off with an ionic compound so that there is conduction. You take sodium or potassium salt of carboxylic acid. And mix it in water, of course. You take a solution of it, then pass electricity. So on electrolysis, you end up getting alkane, which is double the number of alkyl groups that you started off with. So it's RR, like it's just like Wood's reaction where this pairs up. And your side products, you get carbon dioxide and water. So this particular thing, the alkane, you end up getting at the anode. Okay. And the other product like hydrogen and all, you end up getting in cathode. But we'll get that when we get to the mechanism. So if you take R, CO, Na or COK solution, because you pass electricity. Electrolysis matlab kya? Like you have that Daniel cell, right? You take the solution, dip 2 electrodes and pass electricity through it. You end up getting the alkane. So where it differs from the previous decarboxylation is that in this case, the alkyl part of your acid is going to get paired up. You get RR, and all the eliminated ones, your byproducts are carbon dioxide, water, and NaOH. Okay, so note down this thing, like note the pattern, learn it, understand it. Then we'll get to the mechanism. Let me know when you guys are ready so that I can like flip the page and start with the mechanism. I'll also get some water in the meantime. Not this time. Okay, Arnav, Smera, Adit are done. Maybe we should do some X.
The alkane will be at the anode, right?
Yeah. That's why I wrote the anode in brackets. All right. I'm guessing everybody is done by now. Anyone still noting, let me know. Otherwise, we'll go forward. Okay. So Cobb's electrolysis. The raw materials we are taking. So based on the reaction, when it comes to electrolysis, like tell me what happens. So what is the electrolyte in this case? You guys have noted down the reaction, right? So look at
Water.
pure water. Will that conduct electricity?
No.
Mineral water.
What raw material are you taking? Like, what ions do you want so that, you know, they can rearrange and get your final products here?
H plus ions.
You're getting the
Salt.
salt water. So your electrolyte is the, or let's not put CH3 here, the RCOO minus and Na plus or K plus solution. You noted this down, right? You're taking a sodium or potassium salt of your carboxylic acid, mixing it in water, and that's what is being electrolyzed. Your electrolyte, what you're taking as the solution is water plus these ions. Okay. Now, so based on this, in the solution, what cation would you have? What cation will you find?
Na plus or K plus.
Correct. Based on what salt you take, you get either Na plus or K plus. And what is the anion that will be produced here?
COO raised to negative.
Yeah, the RCOO minus part. It's not just CO minus, it's RCOO minus.
For the whole thing then.
Compound. Correct. Okay, so this is your cation, this is your anion. So once I pass electricity through it, okay. The mechanism is going to have, like, because we are breaking the bond here, right? So there's a little bit of rearrangement that takes place. I want you guys to pay attention here, and then I'll give you guys time to note it down. But for now, just focus on what is happening here. Okay. And don't wait till the end. Take it step by step. See that you understand what is happening here. Stop me immediately if there's any part you're not able to get. Okay. So step one. Let's take CH3, sodium acetate only. CH3COO minus is going to dissociate into ions. You get CH3COO minus and Na plus. This is a reversible reaction. So this is what's been happening in the solution. Like, some of them dissociate, some of them associate, whatever. Now at anode, what ion will you find? Which of these two ions will go towards the anode?
Na.
The anions.
Anions. Have you guys forgotten? That's why we call, you know, the negative and electrode as cathode and the positive electrode as anode. So cathode के पास cations जाएंगे and anode के पास anions जाएंगे. This is very easy to remember, no confusion. So based on this, then you can figure out, अच्छा cations अगर इनके पास जा रहा है, मतलब this is a negative electrode. Anions have to get attracted to anode, मतलब this should be the positive electrode. Okay? So at anode, the anions are the ones that's going to migrate. So let's see what's happening at the anode. So this is step 2. This you have CH3, C double bond O, O minus. Anode is positive electrode, right? So there is going to be loss of electrons. The anode is going to attract an electron. So out of all these pairs of electrons, if I remove an electron, what will I get? Will I get a positive compound or a free radical or a normal neutral compound?
A neutral compound.
Okay. So is it going to
Could
be
you
like,
repeat what would you remove?
what other could it be?
Could you repeat what would you remove? Like that.
I'm
what
removing
will
an
you remove?
electron. That's why I wrote minus electron here. The anode is going to take electron. Like that's how electrolysis works. So if I remove an electron from here, like a single electron, what will I get? यहाँ पे excess electrons है ना, इसलिए negative charge है. So I'm removing one of the electrons here. So I'll just write it down and I'll show you this. Rest of it will remain the same, just that this oxygen, instead of having 3 pairs of electrons, it'll have 2 lone pairs and 1 single electron here. So what is this? What would you call this sort of a species?
CH3CO plus.
No, like would you call it a molecule, atom, like cation, anion, free radical? क्या होगा ये?
Cation.
No. Cations के लिए
Radical.
positive. This is a free radical. Now, because it is got only one CH3, we call this the acetate free radical. Okay. Now, free radicals are, because the octet is not fulfilled and it's not like charged or anything, right? So free radicals are extremely violently reactive. So every reaction that you come across a free radical, this will be the case. This is a given. Agar free radical hai, matlab reaction hoga, like whatever they hit, they're going to react with. So this being extremely unstable, especially oxygen being more electronegative, it's going to break this particular bond. So there's going to be homolytic fission over here. Homolytic fission matlab the pair of electrons are going to be shared equally. So एक electron इसमें जाएगा, दूसरा electron will go towards this, and this in turn is going to change into methyl free radical and carbon dioxide, which will escape us, which is one of the byproducts over here. That's how you get carbon dioxide. Okay, so all of this is happening at the anode. So this is like the key step. Like, how is decarboxylation taking place? It's by this is changing into an acetate free radical at the anode, and oxygen especially cannot stay as free radical. Like it's highly electronegative, so it's going to attract electrons. So ये वाला bond में से one electron will go here, because this oxygen needs just one more electron to complete octet, so it's going to take just one more electron and escape as CO2, and this is going to, you're going to get a methyl free radical. Okay, so similarly, we're not going to do, like there's going to be a lot of molecules in the solution, right? We're not going to do reaction on single molecule like that. So whenever two of these free radicals come together, they will attach with each other, and then you end up happening like, then you get, that's how you get an alkane. So two of these free radicals hit each other, they'll be like, hey, we can form a bond, and then the chemical bond will form here.
Ma'am, could you explain the acetate free radical again?
So what part of it do you want, like how it is formed, or what?
That CH3 gives, like, takes one, something like that. What is that?
See, the whole thing is like octet form hona chahiye na. Oxygen ke paas octet nahi hai. It is one electron short. So this is like I want one electron. So this is the bond that breaks. Remember, carboxylic acid may these two, like there is constant resonance in this part of it, so it's difficult to break any of these two. Like oxygen is not going to go off as a single atom. So what happens is, this is the bond that's going to break. Because oxygen needs only one electron, instead of taking both the electrons, it'll leave one with the methyl group. That is what this arrow represents. And it takes the other electron. That's what this arrow represents. And that's how you end up getting carbon dioxide, because C double bond O, C double bond O. Okay. And yeah, so like CH3 is there, instead of having both the electrons, it has only one electron. So that's why this
So
is.
the bond between CH3 and C is breaking.
Yeah. So whenever you come across these curved arrows like these, no? So this represents the movement of electrons. That's what we did in the previous chapter. So if both the electrons are going, you show it using a full arrow, but only one electron is going, matlab half of a fish, like you call it fish hook arrow. Show it like this. Yeah, so like these small curved arrows literally shows movement of electrons. Bond, a single bond, so two electrons are there, one is going here and one is going over here.
We write this down now, right?
Yes.
Okay.
So this is what happens, and you're finally getting your alkane at the anode. And that's like, this literally shows the mechanism why you end up having a doubled up R group. So hydrogen being positively charged, gonna go towards the cathode. That's why hydrogen has nothing to do with it. So two of the alkyl free radicals hit against each other. That's why it's all like doubled up. You get RR.
Ma'am.
Yeah.
So where exactly are we getting the CH3 plus CH3, like two of the CH3 radical?
From here, it's formed over here at the anode.
But how did we get two of them?
How do you do reactions? Like if I take a beaker full of solution, will I have a single molecule or will I have like a whole bunch of molecules?
Bunch of them.
Yeah. So all of the acetate ions will undergo the same process. So you'll have a whole bunch of CH3 produced at the anode. Out of that, like two of them get paired up from the bond. So this is what happens. All of them are happening at the anode. Next, we'll see what's happening at the cathode. We can write this as step 3. Because this happens after step 2. Cool. Who's it? Adit is done. Kaveri, Sanat, and Rishit. You know when you guys are done. Rishit, so Kaveri and Sanat. Cool. Okay. So apart from this, you also have water in the solution, right? So let's see at cathode. So you have water. If water were to ionize, what ions will you get? This will not be at cathode. Like solution may, because you have polarity and all, water also ends up ionizing. Water ionizes into what? What ions? Yeah, H plus and OH minus. So now at cathode, you have these H plus, right? So two of these, like all the H plus will migrate towards cathode because cathode attracts cations. And cathode is negatively charged. Like the reason why it attracts cations, it has a whole bunch of electrons. So these two end up joining and escaping as hydrogen gas. And in the solution, so यहाँ का Na plus is still in the solution and यहाँ का OH minus is still in the solution. So the Na plus and OH minus, you'll be left with NaOH in the solution. Okay. So that is the story of all of the atoms and ions that you get in the whole, in this whole thing. So just to summarize, what happens is at cathode, what gases are produced at the cathode? So go over the whole reaction. Tell me what all gases you get at the cathode.
H2.
H2 gas.
Hydrogen.
Yeah.
Yes.
And at anode, what all gases do you get?
Carbon dioxide.
CO2.
CO2.
Okay. Only CO2?
Here we got like ethane as well,
Huh.
like in this particular reaction.
Yeah,
I free radicals, no?
alkane.
Oh yeah,
You
alkane.
get at the anode. See, this whole story is taking place at the anode. So first step से CO2 produce हुआ और यहाँ पे ये वाला alkane भी produce हुआ. So both these gases, you can collect it at the anode. And in solution, you'll be left with NaOH. Okay. So you taking just the solution like water mixed with the carboxylate salt, and once you pass electricity, all of this is going on. So you can see how each atom, each ion, what sort of changes are taking place, and yeah, that's how you end up getting each of these byproducts.
Ma'am, can you like go back to the previous page once again? Okay, done.
How quick is this reaction? Like, does it happen in like proper steps, or like while it's happening, it's all like simultaneous?
Simultaneous. So simultaneous in the sense, obviously, in order to get your methane, this step has to take place. See, it's all in a matter of like nanoseconds, microseconds, I would say. So as soon as the salt touches water, gets into water, this dissociation, the ionization is going to take place. And after you apply electricity, that's when these other steps at cathode and anode reactions are going to take place. But yeah, so free radicals, ions, they cannot exist independently. They can exist only in solutions. And especially when there's like opposite charge right there, no, it is definitely going to, like join together. The reason why solution may say that these ions exist is, again, that's why the reversible arrow is applied here. It's not that they dissociate and stay as ions permanently. So they dissociate, and then opposite charges attract, they associate. So at one point, this molecule is dissociating, at another point, this one is dissociating. Like everything is in constant motion at all times. So when electricity is applied, that's when, the oppositely charged ions separate out, and that's when the hydrogen is gonna migrate. And after that, once it's got its electrons escaped as a gas, it cannot form water again, right? Like this is like a permanent thing. So just to give you a visual of, like what exactly is going on in the solution. So at an atomic molecular level, it is obviously like in a matter of microseconds. But again, it is also dependent on the collision between the correct particles. Like these free radicals, if it collides against, I don't know, like an OH minus or something, that's not going to be a significant change. If it collides against another CH3, then it forms ethane and it escapes as a gas. So to get a considerable amount, then you're going to have to wait some time, like depending on the quantity you took. If you did it in a small beaker, maybe a couple of minutes or so. If you did it in a huge reactor vessel, then some more time. But atomic molecular level, it's pretty instantaneous, like dissociation, association, all of that. Okay. Again, based on the kind of alkane that is being produced, what is the drawback with this method? Like what is let's not say drawback, because it's a good convenient method to produce alkane. What is the limitation with this method? Can I produce propane using this method?
No, because the alkanes only double. Propane has like 3 carbons.
Yeah. So you cannot produce odd number, like alkanes with odd number carbon atoms cannot be produced. So that's a limitation with this. And that's it. So
What
all
about higher order alkanes?
same methods.
Like, can those be produced?
Yeah, as long as they have even number. Like if you end up taking sodium laurate. So from lauric acid, like sodium laurate. So laurate is, I think, C12, if I remember correctly. So you apply this method with sodium laurate, then you end up getting like again carbon dioxide aa raha hai na, to -1. So C11 will join together. So you end up creating an alkane with C22H 44, 46. The mechanism is going to be the same with different reactants with the different number of carbon atoms. The issue is that, again, electrolysis, right? So if you have extremely large alkyl chains, it is going to affect the rate of the reaction. So it is bent on this dissociation, right? So if this dissociation is not as fast, your rate of reaction will be reduced. Second is the migration of this anion towards the anode. So if you have a really large molecule, it's going to take time for this thing to move in the solution towards the anode. So there the reaction is getting slowed down again. So production of the alkane can happen only after the anion gets to the anode. So if that's not happening, then you won't get your alkane. So theoretically, it's possible, but it's going to be a little more difficult because of all these factors, higher order ones.
Ma'am, I had a doubt. So, what did you mean by when you wrote in solution? So, is it present in the solution?
Yeah. Like you don't get NaOH specifically at cathode or anode. Like in solution, you have these ions. So you end up having NaOH aqueous. Like beaker may, if you take this liquid and test what it is, it's a solution of sodium hydroxide. Okay? Can we do
There's
the
only one limitation.
yeah? And as I mentioned, like higher order, like for specific cases, yeah, depending on what their issue is, it might be, but generally, yeah. So if we're done noting it, again, tell me to go back. As always, practice reaction.
Ma'am, can you like just go back for a second? Done, ma'am. Thank you.
Give me the IUPAC name of the product this time, okay? What product will be formed if I took this? So I did Cobb's electrolysis on this particular compound. What is the product that what is the alkane, the IUPAC name of the alkane that I get? And of course, you have your regular side products.
Ma'am, could you go back to the previous slide?
More. Sanath, no, wrong answer.
Ma'am, could you like go to the next page.
Kaveri had asked, no, you done with this, Kaveri? Ritu got it, yes. IUPAC name, so you have to mention the common name. So यहाँ पे, like you guys learned that R like the two alkyl groups are joining and forming a bond. So pay attention to where the bonds are being formed. Like what would be the structure of this R and R? Structures are very, 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 very important in organic chemistry. Like so that's why you had isomerism and everything. So Ritu is the only one who's given the correct answer so far. Sanat, check the. Rishit, why? I've changed this thing, like it's not acetic acid anymore. See what alkyl group is there here. See, when I took CH3COONA or C whatever, CO minus, the bond broke here and the two CH3 joined to form ethane. That's what happened in the previous thing. You had the methyl free radical. So same pattern over here also. Yeah. Sanat, now you got it. Smira, no, check again. Ritu and Sanat have gotten it. So I've given a hint also here, like with acetate, this is what happened. So apply the same thing to this other compound also. Smera, yes, now we got it. So Ritu, Smera, Sanat got it. Kaveri, Rishit, Arnav, Adit, where you guys are?
I think I'm stuck.
Same.
Like I know it starts with potassium and CH3 again that is ethane, right?
Guys, you don't have to work out the whole mechanism. Like when you have a question like this, where you're simply being asked about the product, right? Look at the overall pattern of the reaction. So even if you go by the mechanism, you know that this whole C double bond O is breaking off over here, right? तो यहाँ पे C double bond जो है, इसके पहले जो भी है, that is the one that's like joining together to form the alkane. तो यहाँ पे alkane form करने के लिए, where does it break off? Like, let me number the carbons. So between 1, 2, 3, and 4, which bond should I break to get my eventual alkane?
2 and 1.
2 and 1 is correct. To write the structure exactly. So 1 breaks off. So what you'll be left with is CH hai idhar, and rest of it is not affected. जो है वैसे ही रहेगा. After it broke off, क्या हो रहा है? 2 of the same things are joining together here. That's what's gonna happen. Same thing, CH है, and then ऊपर नीचे CH3 है. आ गया product. So now you have to do is इसका IUPAC name क्या है? So that would be your answer. Kaveri and Arnav, what about you guys? You've been kind of quiet.
Yes, but just typing.
ठीक है. Kaveri? There you go. Arnav has sent the answer. Yes. Rishit, you also got it correct. Other than Kaveri, what's going on?
Oh wait, should I resend the answer and wait? Okay.
Oh, अच्छा आया नहीं है यार. Anyway. Is Kaveri stuck again? So, Sanat and Smera, like both of you did the same mistake pehle. What did you do? Like, did you not? Like,
I just combined CH3 and
No, I
CH3.
didn't see the structure. I just combined.
Yeah.
you just saw there were 3 carbon atoms and then you just put it there. The structure is quite important because that's why the mechanism is there, right? Like that's why you learn where the bond breaks and how those electrons move. I think there's some issue with Kaveri's network. Got disconnected earlier. All right. Do you guys want to do another of these questions? Or should we go to the next method and do all questions together?
Either way is fine with me.
What's the next method?
I'll do one thing. I'll give one more question that basically summarizes whatever we did today. If I take I know we've done this before, but anyway, C2H5COONA. And then two things, okay? So one, I heat it with soda lime. And the other, I put it in a solution and do electrolysis. In this case, I get product A. In this case, I get product B. So identify A is what alkyne and B is what alkane and B is what alkane. So this particular carboxylate salt, I heated some of it with soda lime and I got A. But if I electrolyzed its solution, I got product B. So identify what A would be and what B would be.
We
The
just
whole
have to write the
product
names of the alkanes and not the gases and byproducts, right?
Yeah, just the alkanes is sufficient.
Okay.
I'm sorry, what do we need to do?
Identify A and B. So these are the reactions. Yeah. Arnav, you got confused.
Sorry, ma'am.
Adat, you also got confused.
Yeah, I just rechecked it again, like by calculating myself.
The second time you sent, A is correct. Sanat, A is correct. Ritu got both A and B. Very good. Sanat, B is also correct. Smera got both A and B. Nice. So Ritu, Sanat, and Smera got both A and B. Good stuff, you guys. So Adat, A, you got it. B, like the reaction is right here. You should get it now. Nice. Adat also got both A and B. Absolutely correct. Arnav and Rishit. Rishit, yes, you got A. Just identify the alkanes. The byproducts are fine, not necessary. So both A and B are alkanes. Just give me what alkanes you get. All right, Kaveri. Yeah, figured because could not hear you at all. That's perfectly fine. You can use the chat if you have any questions or anything. Okay. Now that you have like took down the notes and all of that, like go through the reactions and answer this question. So C2H5COONA, if I heat it with soda lime, what alkane will I get? Identify A. And if I do Cobb's electrolysis, then what is the alkane that I get, which is B? So identify A and B. Arnav, A is correct. You identified that. B is you just put C2H5, which is an alkyl group. Rishit, you did. So what alkane is that? Give me the name of the alkane or like the complete formula. You just give me the structure. You figured it out. Just give me the name. Arnav, see, this is R and R. It doubles up. So you identified the R part of it correctly. Give me the final product. So A, much everybody has identified it. It'll be C2H6. So you just need to focus on what is there over here. Soda lime ke saath, it's a direct just addition of hydrogen. C2H5 hai, to C2H6 ho jayega. And the second part of it, Rishit, you were almost there. Cobb's electrolysis mein this doubles up. So if it is C2H5, the same thing gets attached C2H5, which means it's the final product is C4H10. So in this case, you get ethane. The required alkane was ethane, and the required alkane here is butane. Okay. Simple. So just get the crux of the logic. यहाँ पे soda lime मतलब the number of carbon atoms does not change. So 2 carbon atoms के साथ alkane is ethane. Electrolysis मतलब this becomes into 2. So अगर 2 है तो 4 हो जाएगा. So what is the alkane with 4 carbon atoms is butane. Okay.
What did you say for soda lime?
Same number of carbon atoms. So 2 carbon atoms. यहाँ पे alkane will also have 2 carbon atoms. So based on that also you can figure out which alkane it is. Okay. All right. Final method. So that's all with carboxylic acid. So this is like the most, like you can think of it as another method is from carbides. Okay. Have you guys ever heard of what is a carbide before? Anywhere?
No, ma'am.
No? Okay. So it's carbides are basically when carbon forms compound with metal. Let's say it forms a binary compound with metal. Binary matlab it's simply compound between carbon and metal. Like just say if I have NaCl, there is metal and there is chlorine. So this we call it a chloride. Right? Similarly, when we say oxides, it's basically metal plus oxygen. It's like CaO, it's metal and oxygen. So this is an oxide. Similarly, when you say carbon, it's just carbon plus metal. So examples of carbon, you have aluminium carbide, so that's Al4C3. On hydrolysis, so that's like basically breaking it up with water, reacting with water. You get again, it's like an exchange reaction, AlOH thrice and methane. Similarly, another is beryllium carbide, B2C, Be2C. And on hydrolysis, same thing, BeOH twice and methane. So again, the special note with this particular reaction is can only produce methane. So you have some reactions where you can't produce methane, like Wood's reaction. So this is going to produce only methane. The reason is that like in carbides, you don't have carbon linking up to form a long chain. So each carbon is like an independent carbon molecule. Hydrogen joins up to it and you get methane. Yeah, Sana, did you have a question or something?
No, ma'am, I unmuted by mistake.
Yeah, so these are all the preparation methods. It's 4 o'clock now, 5:30, 1.5 hours, right? properties we have? Substitution.
Ma'am,
Yeah.
so our ma'am told in the exam the portion has not yet given, but ma'am told we will have hydrocarbon, states of matter, thermodynamics, and
Equilibrium.
block.
Oh, S
I
block.
think S block. Yeah, S block. Only one group, that too, which is there in the 12th class. I think group 15.
You're in group 15. Wait,
Yeah,
S
ma'am
block
told.
and group. You're not doing group 30.
Sorry, not S, not S. I think P.
P block. P block.
Yeah,
group
P.
15.
P,
You're doing
group 15, which is there in the 12th class.
Yeah. So you're doing 13,
Yeah.
14, 15 then.
Yeah, I think so.
Yeah, but I think we just did 15 for now.
13 and 14 you haven't done yet.
I don't think.
Like, have you studied aluminium ka group and carbon silicon ka group? Like boron, aluminium.
No, I don't think so. I think it was only 15.
Okay. No S block, right? Only P block and group 15.
They have started
Yeah.
with P, maybe in the later, maybe before the finals, they will also do all of them.
Cool. Yeah, inorganic part group, like once you have the clarity, let me know. But otherwise, you have hydrocarbon, states of matter, thermodynamics.
Hydrogen we don't have because ma'am said that there's some presentation for hydrogen, so we won't be having that in any exams.
Yeah. No, hydrocarbon, thermodynamics, and states of matter. Okay. Okay. We'll start off with the chemical properties. Again, as always, I'll give you guys a list of MCQs. You guys do the questions like after this. Okay. So before we go to the chemical properties, we look at some of the physical properties. What all do you know when it comes to physical properties of alkanes? Like you have come across methane, butane, all these gases, right?
They don't have a sense of smell, nor do they have
The
color.
first four are colorless gases, then liquids like pentane and hexane, then they become solids as they get higher order.
There you go. So first thing is, let's look at the physical state. So the smaller ones are gases, and as you keep adding the number of carbon atoms, as you keep making it heavier and heavier, then you get liquids, and eventually you have like waxy solids. So if you want to know what sort of solids, they are not crystalline. When they solidify, you can think of it as candle wax or ghee, petroleum jelly. Like you guys must have seen Vaseline, right? That's a perfect, that's a perfect way to talk about it. So when alkanes solidify, they're gonna feel like petroleum jelly, Vaseline, not the lotion, the proper jelly, like the waxy solid. So smaller ones, matlab C1 to C4 are gases, and liquids C5 up to C16, 17-ish, and then greater than C18, they end up being solids. So based on this, what can you say about the trend of melting point and boiling point?
The longer the carbon chain, like the higher the melting and boiling point.
Yeah. So simply put, you can say melting and boiling point increase as the as the number of carbons increases. So the higher carbons all have greater melting points, boiling points, and the smaller ones will have lower melting and boiling points. Okay. So the kind of questions like this is quite important because you will get questions based on, like MCQ here. You'll be given butane, pentane, hexane, heptane, arrange in increasing order of melting points. Then you'll be given 4 options and you'll have to choose. Yeah, that way. These trends are important. Okay, so between butane, pentane, hexane, heptane, which one will have the highest boiling point?
Heptane and what was the last option?
Butane, hexane, pentane, and heptane.
Heptane.
Heptane, yeah,
Okay.
correct. So higher the number of carbon atoms, higher will be the boiling point. Simple. Now, what about these 4 options? Suppose I have pentane and pentane, isopentane, and neopentane. Which one will have highest boiling point? Which one will have lowest? Like what will be the trend in boiling points between these 3? Or will they have equal boiling points?
They will have equal now because like all of them are pentane.
According to molecular mass, yes, they're ideally supposed to have equal, but they will not have equal boiling points. What is the point of difference between N-pentane, isopentane, neopentane?
And pentane is like the normal pentane structure, straight chain. Iso is when one of the carbon is like below 1 carbon. And in neo, it is 2
Like
carbons
dimethyl
are
propane.
up and down.
Yeah. So there is like basically if I ask you about point of difference, you can say that structures are different from each other. That is correct. So when we talk about boiling point, melting point, it is literally change in the state. So solid may you have like all of them arranged in a rigid structure. And as it turns into liquid, they loosen up slightly. They're still close to each other, but they can move against each other. And then gases, matlab, the space should increase very widely. Right? Now, if you look at the reverse process, so being a solid, matlab, all of them should be packed closely together. That way, will all of them be, will you be able to pack all of them in the same way, or is there going to be a difference in their arrangement when they're a solid? Like you guys have played with Lego blocks and bricks, right? So imagine you have a block like this, which is a straight chain. And then you have a block with a thing like this. And then this is a block, which is kind of like this. So will you be able to arrange all of them? Will you be able to pack all of them nicely, neatly in the same way? Or will there be a difference in the arrangement of their solid structure?
There would be a
Solid
difference.
There would be a difference because solids are more compact, like the molecules in it, unlike the gases are more free. So
Yeah. So in their solid state, there's going to be a difference how you stack them up one over the other. Huh? So because of this difference, the conversion between solid to liquid, like how much energy you have to give it, completely depends on how they are stacked here, how well, like how tightly they can be stacked there. So based on that, there is going to be a difference in the melting point and so difference in the boiling point between these 3 also. So neopentane will have the lowest boiling point compared to isopentane compared to n-pentane. So as a general rule, if you're comparing any set of isomers, so if there is branching, that decreases the boiling points and melting point. Yeah. So greater is the amount of branching, the lower will be the melting point, boiling point. So neopentane will have the lowest melting point compared to iso compared to N. The reason for this, like why branching decreases the melting point, relates to the surface area of the overall molecule that's available. So we will be discussing, we'll be getting into more of this when we actually talk about this change in the states of matter. So in the chapter states of matter, we'll go deeper in this.
Ma'am, can you go to the previous slide?
So you can note down ye wala part like physical state. So it'll increase with the number of carbon atoms. You can roughly mention like C4 tak you have gases, then C5 to 17 liquids, and higher 18 and above you have waxy solids. So all of these obviously is at room temperature. 16, 17, 18, there'll be a slight variation because obviously Earth maybe room temperature will vary with season and everything. But generally, this is like the thing observed. And another point you can write right below it is branching decreases the boiling point. So you can write both the points together and you can write this as an example. So more is the number of branches, lesser is the boiling point. Yeah, so once you're done writing this down, I'll give you guys 4 more options. Give me the trend, like the order of the boiling points for those, okay?
Ma'am, I have another quick doubt.
Mhm.
Like even though like neopentane has a super low like boiling point, it's still like more than butane, right?
Yeah.
More than N-butane or neobutane?
More than any butane, because molecular mass itself is changing, no? So higher the molecular mass, higher is the boiling point. So just give me the order, like you can write it as A, B, D, C, like something like this. Yeah, whatever the order needs to be.
Ma'am,
Yeah.
I might have forgotten a bit, but for the D1, since it is in like the CH3 is outside the bracket, will that be, wait,
This simply means you have CH3 and then the CH2 is repeating 4 times. You have 4 CH2s over here. And then finally you're ending with CH3.
okay, got it.
Good. Ritu and Sanath have already sent in their answers. Good. Arnav and Rashid, incidentally, you guys sent the exact same answer. I just go through it. Like, see, first, you need to consider this. Number of carbon atoms is more means the boiling point also will be more. And then if you run into a situation where, oh, dono mein same number of carbon atoms hai, then you need to look at the branching. So Smera is correct. Rishit, the first and last are correct. Beach may check again. You need to consider two factors. One is the number of carbon atoms. इससे एक order set हो जाएगा. Then if you're confused between two, then you look at this. No, Adat. Arnav also, your first and last are correct. Beach में जो है, compare the number of carbon atoms, no? Same amount of branching, but number of carbon atoms is different, no? Rishit, yeah, the final abhi jo bheja hai, that is correct. Adat, first number of carbon atoms, then you look at the branching. Arnav, what you sent abhi is correct. 421. Yeah. Adat, close. Again, first and last are correct. Beach mein jo hai. So, based on number of carbon atoms, यहाँ पे कितने carbon atoms है? Compound A में 4. Compound B में कितने carbon atoms है? How many? So this is C4H10. What is compound B? Adat?
3.
How? 1, 2,
Oh no, wait.
3,
4.
4. This is also C4H10. C में कितने carbon atoms है?
5.
5. D में कितने?
6.
6. So based on this, you'll get an order. Now A and B have same number of carbon atoms. The difference is that A is straight and this is branched. So
B will be first.
So B will be lowest. उसके बाद आएगा
A, then C, then D.
A, then C, then D. That's it. That's how you go about it. Very simple. First, look at the number of carbon atoms. Then, if you're confused between two, then look at the branching. That's all there is. Okay. So any more confusion? Like if you get a similar question, will you be able to do it, Abhi? So number of carbon atoms also, like don't think of nomenclature ki acha longest chain is 3. This is purely for molecular mass. Basically, if the molecular mass increases, the boiling point increases. That is the reason you count acha total, like molecular mass is technically same for both. That's why we count these as equivalent. Okay? Guys, okay, got it?
Yes, ma'am.
Yes, ma'am.
Okay. All right. So, yeah, this is all about physical state, boiling point, melting point. Next, let's talk about other properties. You guys know colorless, odorless. So Adit, one small correction. These gases obviously don't have a sense of smell. It's the fact that we cannot detect it. We cannot see it. Okay. So we don't have the detectors for these gas. Okay. Next, what else? Color, taste, tasteless, odorless. Density. So considering they're like gases and liquids and all pretty light, what do you think their density is compared to water? Are they heavier than water, lighter than water?
Heavier than water?
Alkanes, no? So let's compare the simplest alkane. Okay. Simplest alkane kaun sa hai?
CH4.
CH4.
CH4 methane.
What is water is H2O. So density is mass by volume, right? So if you compare, what is the mass of CH4?
16.
16.
And water?
18.
18.
So if you look at this and look at the ratio, kiska density is zyada ho sakta hai, kiska, which will be heavier, which will be lighter?
Water.
If divided, then water will have more.
Yeah. So in general, alkanes are lighter than water. So all the alkanes, whatever alkanes you take, if you put it in water, it's going to float on water. Yes. You might think, okay, this is, we are considering methane alone. What if we take butane? So obviously molecular mass is going to be greater, right? So this is 18, this is going to be 12 into 4 plus 10. So 48, 58.
The
Right?
volume would be greater as well.
Correct. So, but because more number of carbon atoms, matlab, volume is also proportionally increasing. So in general, density of all the alkanes are going to be, they're all going to be lighter than water. Yes. And also, what do you think would be the trend within alkanes? So do you think density increases with molecular mass, decreases, or is it going to be constant?
Increases.
Yeah, density increases as the number of carbon atoms increases. Just like boiling point, melting point, this is also like a direct proportional. Yeah. So in general, alkanes are lighter than water, but within alkanes, if you compare methane with butane, this is going to be more dense. So density increases as the number of carbon atoms increases.
Ma'am.
Yeah.
If we increase the number of carbon atoms, will that? So basically, why is it lighter than water? All the cases of it will be lighter.
Yeah. So if you increase the number of carbon atoms, mass is increasing, but your volume is also increasing proportionally, right? So water is just H2O, but your butane is considerably a bigger molecule. So with mass, your volume also increases. So overall ratio, if you take mass upon volume, your density will still be lesser than water. There's another reason why water is more dense, which ties in with the next physical property we're going to talk about. What do you think of the polarity of alkanes? Are they polar or non-polar? Dipole moment and all you've studied, like chemical bonding.
Non-polar?
Okay, Ritu saying non-polar. What do you all think?
We are lesser than the water, right? Here. And alkanes.
No. In general, alkanes, if you take any alkane, are they going to be polar molecules or non-polar molecules?
They
Here
would
is
not be.
the polarity, they are all non-polar. So all of them will have zero dipole moment. Yeah. So that is another reason why water has more density also. So if they're all non-polar, the forces of attraction between each of these molecules is going to be lesser. So they won't be as tightly packed as the water molecules would be. So that's another angle you can look at, you can think of. So polarity, they're all non-polar, they have zero dipole moment. So the only forces they have between them is only van der Waals forces, which is why again ties in with your boiling point, melting point. In general, they have low boiling and melting points. Rishit is saying, since it's between carbon, there is no polarity, right? That is partly correct. Yes, between carbon, there is no polarity. Hydrogens may, there is going to be some amount of polarity, carbon-hydrogen bond may, but because in the end, it all tends to be symmetrical, pura tetrahedron hai, they all end up cancelling each other and your net zero dipole moment hoga. So symmetry is one, and again, carbon. So that's another reason. Alkanes, remember, they're all hydrocarbons, carbon and hydrogen. So between the carbons anyway, there's no polarity. Hydrogens may each bond is polar, but net, they all end up cancelling each other out. So you end up with zero dipole moment. Okay, so these are the four physical properties we'll talk about. Melting point, boiling point, like that relates with the physical states of things. And they're colorless, odorless, non-polar. Density, they're much lighter than water. Within alkanes, density increases as the number of carbons increases. Okay. Cool. So note this down. Once you're all done with it, we'll get started with the chemical properties. So I don't think we'll finish all of the chemical properties today. It's already 4:30, we have an hour. I'll do the most important ones, which are the substitution reactions. And the rest of it is all very, very easy. Combustion, controlled oxidation, isomerization, aromatization, pyrolysis. These are like, there's only one major reaction, which is substitution, different types of substitution reaction. That is the only major thing. Rest of it is all, I'll just give you guys equations, you'll get the hang of it. There's no mechanism or anything to remember. Adit and Arnav are done. Both of you had reacted. Kaveri, how's it going? Is it all sorted now? Or the issue is still there? seems to be there. Still, you're still on mute, Kaveri, so in case you're trying to speak. All right. So now we'll get started with the chemical properties. So chemical properties, there'll be more reactions now, but this time we're gonna look at reactions that you start off with alkanes, you make them react with different things and see how they behave. Okay. In general, now, because this is the first set of chemical properties we're talking about, organic may the type of reactions that you'll study about is going to be completely different. We're not going to have combination, decomposition, displacement, and all of that. Here you're going to have addition, which we saw addition, hydrogenation reaction was a type of addition. Then you have elimination, which we will do in the production of alkenes. You have substitution. This is like a major. You have nucleophilic, electrophilic, free radical, depending on the mechanism. So this we'll get into properly. And you have rearrangement. So out of these four, these three you will be coming across quite frequently. We'll be looking at the mechanism of each of these in different contexts. Yeah, so just be familiar with the names and like what's happening here. Okay. Apart from that, you have like these named reactions and all, but we'll get to that when we get to it. So first reaction we'll talk about, alkanes undergo substitution reactions. Yeah. So depending on what we are substituting with or like what route it is taking for substitution, you have different types or names of substitution reaction. So alkanes, this is like the most famous reaction of theirs. We look at halogenation. So the name itself should give you a hint what it could be. So what do you think is going to happen in this reaction when we are calling it halogenation?
Halogens like chlorine, fluorine, bromine.
Substituting hydrogen with a halogen.
There you go. Substitution reaction hai. We're literally calling it halogenation. So you take an alkane, react it with a halogen, you end up getting a haloalkane plus HX. So haloalkane is basically your RX. Okay, halogen, you take X2. So basic things. Okay, so another important information about this reaction is that you absolutely need to give it some energy. This takes place only in the presence of light, or you heat it to 573 Kelvin, is it? Yeah, 573 to 773 Kelvin, between these temperatures. The easier way is to just do it during daytime. Like if you want to control it, then just by controlling the amount of light, you can control how much this reaction will take place. You can control the extent of this reaction. If you just do it in the middle of the day, 2 p.m., stand near the window, take the test tube there, it is going to go out of control. You won't end up with explosion or anything, but like if you're aiming for a specific product, you're not going to get that.
The X in both the cases are halogen, right?
Yeah. How we use R to denote the alkyl group, X is usually used to denote halogen. So whenever you come across X in any reaction, it means it's an halogen. In question, don't confuse it. Like you might get questions like a compound X, there it's a variable. But generally, like textbook may, when you're looking at mechanisms or general reactions, X is usually used for halogens. Okay. Before we get into the mechanism of it, there's some notes about it. Okay, so like one thing you guys need to note is the order of reactivity. So order of reactivity, like we look at alkanes also and halogens also. For a specific alkane, if you're comparing it between the 4 alkanes, what do you think will be fastest, fluorine or iodine?
Fluorine?
Fluorine, yes. So fluorine will be the most reactive. After that, chlorine, then bromine, then you have iodine. So within halogens, this is the order of reactivity for this particular reaction. And the order of like the rate of replacement of hydrogen. So if I consider, let's say, primary, secondary, tertiary, which will be the fastest, primary, secondary, or tertiary? In which case is hydrogen replaced the quickest?
Primary?
No.
Tertiary.
Tertiary will be the quickest, followed by secondary, followed by primary. Okay. Why? Like once I get into the mechanism of it, it'll start making sense. I'll just write it for uniformity's sake. Tertiary first. Yeah. And so another bits of information about it is like fluorination. Now, because it is the fastest, this reaction is very, very violent. And this is so violent and so reactive, it does not require light also. So this reaction is usually done in the dark to have some measure of control over it so that things don't explode all over. And this reaction is very, very rare. Like if you want to fluorinate alkanes, this is not how you go about it. You have better controlled reactions, if at all. And when it comes to iodination, so that's if you're looking at iodine ka substitution, this is as reactivity decreases, it is very, very slow. It is slow, becomes reversible. It's slow and reversible. So if the reaction is slow, the HX gas is not escaping fast enough. So this is gonna react with haloalkene back, and then the reaction is going to be reversed. So it requires, like it needs an oxidizing agent. Like HNO3 or HiO3.
Ma'am, it is reversible, meaning like after we combine it with an alkane, we can get back the halogen.
Yeah. So the Hi that will be formed, it reacts with the CH3I or C2H5I, whatever. And then the reaction is just not going to go forward at all. It will be reversed. So you use an oxidizing agent to take away the HX. Like once you take away this HX, it's not gonna, like there's going to be nothing to react with haloalkane, right? So you get your product properly. Okay, Adit is done. Arnav, okay. Ritu, Sanat, Rishit, and Kaveri. Is she done? Okay. So now we're gonna talk about the mechanism. So this is substitution reaction. Mechanism में there are 3 major steps. So step 1, the first step, initiate 4 major steps you can think of. You see. So this is the initiation. Kind of logical, right? Starting is like initiating. कैसे initiate हो रहा है. Then step 2, we have propagation. So again, very commonsensical, like कैसे continue हो रहा है, like how is the reaction propagating so that all the molecules are converted. And finally, like this will have multiple things. And the third step is termination. So again, as the word says, how is it terminating? Like how is the reaction ending? How can it end? Okay. Yeah, there's the 3 steps. So initiation, like this reaction starts when the halogen molecule, let's say if you're taking chlorine molecule, in the presence of, like, because of the light, this bond breaks and you end up getting free radicals. Okay, so this is like the important initial step for this reaction to take place. So in the presence of light, the halogen molecule splits. So do you guys remember the name of this type of splitting?
Homolytic fission.
There you go, homolytic.
Cleavage.
So it's going to be homolytic fission and splits to form halogen free radicals. So that is the reason this like halogenation, because halogen is being substituted. This is also called, like the mechanism for this is also called free radical substitution. Okay, like substitution में ही depending, I told you, right, like depending on the mechanism, depending on the reagent, like what is attacking the compound, you have different types. You have electrophilic substitution, nucleophilic substitution. So this particular type of substitution, if you're looking at halogenation of alkanes, that follows free radical substitution. It's a type of free radical substitution reaction. Okay. The reason why we call it this is you get free radicals. That's what like pushes the reaction forward. All right. So once it's initiated, how is it propagated? So what happens is you have chlorine free radicals. Like again, free radicals are very, very, very violent. They're so aggressive. Anything they hit, they're gonna like change things up. There's gonna be a chemical change there. So when this chlorine free radical hits the alkane, let's say CH3 that we CH4 methane ka molecule that we have, this ends up substituting one of the things. So you get CH3 methyl free radical and HCl. Yeah. So then you have another, like this free radical has produced another free radical. So again, this free radical, methyl free radical, can hit another chlorine molecule that is there. Then you get CH3Cl and another chlorine free radical. So again, this step, again, this chlorine free radical can hit another molecule. So this keeps repeating until all of the things are this thing. In the meantime, this is also there in the same container, right? So let's say the CH3Cl comes across, hits another chlorine free radical, like if there's enough energy between them and everything, you can have another step of substitution also taking place. You get CH2Cl free radical plus HCl. And this CH2Cl can hit another, CH2Cl2 plus chlorine free radical gives CH2Cl2 plus so basically whatever free radicals are there, depending on what they are hitting, whether it's a chlorine free radical, whether it's a fresh methane molecule, whether it's one of the product molecules, whatever they may be hitting, they will end up producing a new product and then keep continuing on. So that is the reason the availability of light is quite important, because if you have a lot of light available, there's going to be a lot of free radicals produced. And once the free radicals are produced, there's no telling what products will be produced, because you can't control the motion of these atoms and radicals and ions within the test tube. Whatever is there, they're going to hit that other molecule, produce a new radical, and then produce a new product. That's why this step is called propagation, because that's how this reaction keeps continuing. Yeah, Rishit?
Ma'am, so what exactly repeats? The Cl plus CH for collision? I mean combination, or the CH3Cl plus Cl radical?
This one. So this chlorine radical can hit a new methane molecule. Then these two steps keep repeating. So this is another alternative, like also the chlorine radical may also hit a new product molecule that is formed. So in which case you're going to get a dichloro substituted product that way. Yeah.
Got it.
Yeah. So this reaction keeps on continuing until, like, if you want to terminate this reaction, you gotta not have any free radicals being produced. So when does this reaction end? So this reaction ends if a chlorine radical combines with another chlorine radical, forms Cl2 back, or maybe there's a chlorine radical and a methyl radical forms CH3Cl, or maybe a methyl radical combines with another methyl radical and forms ethane. Yeah. So there are lots of possibilities of products in this kind of a reaction. So you don't, like, free radical substitution is not used for any purpose at all. Like, unless you don't mind getting like a mixture of products, you don't really use it in a lot of places. You may use it to produce chloroform and then separate out, and then you have to invest in, like purifying your products that are formed to get pure monochloromethane or dichloromethane or trichloromethane that way. But generally, industrial preparation and all, like free radical substitution, is never used, precisely because you cannot control this reaction. You cannot control what radicals are produced and what products these radicals produce. Yeah, you
So,
cannot.
ma'am, the process will terminate even if one of them is happening.
It depends. So basically, this is to show that, see, you have methyl radical produced and chlorine free radicals produced, right? So so the difference between propagation and termination is the reaction will continue if another free radical ends up being produced. And the reaction will end when, the reaction between free radicals does not produce any more radicals. You're getting like proper molecules in the end. Yeah, so if you end up getting more free radicals, then it's just propagating the reaction. But if a free radical ends up combining with another free radical, combine both of it, then you come to the end of the thing. Yeah. Okay. And any questions about this whole mechanism, like what free radical substitution is and how it goes on and all that? So simple way to identify what step like a particular stage is if like the division of chlorine is always initiation, you get chlorine free radicals. Suppose a particular half reaction ends up producing more number of free radicals, that is like reaction is still propagating, so that will come under propagation. If the products contain completed products, like no more free radicals, completed molecules, then that is a step of termination. Yeah, so suppose in case you get a question asking you to identify what step of free radical substitution it is, whether it's initiation, propagation, or termination, observe what is happening in the reaction. So if it is pure molecule to radicals, it's initiating. If a radical is producing another radical, then it's propagating. Reaction still continues. This will again hit something else and form something else. But if you're getting complete like final products in the equation, then that's termination. You don't have any more radicals being produced. That's the end of the reaction. Okay. Guys, yes, no, like respond something, no, otherwise I'll keep repeating the same thing again and again.
Yes, ma'am.
Everyone, like I've had a talk with you guys about this.
ma'am.
I can't see your face, so I don't know.
I'm noting it down right now. Yeah, just a minute.
Okay. Okay. So say something like, okay, you're still noting down, you got it. Cool. So note it down, like let me know when you're ready to go to the next property.
Ma'am,
Yeah.
so basically it will terminate if no free radicals are produced, right?
Yeah.
Okay.
If there are free radicals, equation will go on, reaction will go on. No free radicals means end of the reaction. Smera, Arnav.
Yes, ma'am, done.
So Sanat and Rishit, once you guys give me the go ahead, we'll go to the next equation. Kaveri, I'm looking at the chat, okay? Like if you need some time to have any questions, like put it in the chat. Halogenation is when we substitute with halogens. Another equation we look at is sulfonation. Okay, what do you think sulfonation is? What group are we substituting now?
Sulfur.
Sulfur.
So this is when hydrogen is substituted by sulfonation में you have HO3 group, SO3H. Okay. So this, just like how COOH is carboxylic acid, right? So that way SO3H is sulfonic acid. This is also a very like sulfonic acid. Basically, you take off H, put Na. Like iske salts are what you find in shampoos. So just take any of your shampoo bottle. If you look at the ingredients, you will find sulfonic acid, sulfonates. Again, if you're looking at a generic shampoo like Head and Shoulders and all, like if you're looking at sulfate-free stuff, then you won't have this. But till like a bunch of years ago, even now, if you just get something from regular department store and all, like the non-biotech, like branded ones, you will have sulfonic acid. Laurates and sulfates are what you find. So yeah.
Why did you cancel it?
No, like the more recent one, like if you're looking at, if at all it happens to be sulfate free and all, you won't find it. But if you're using like, I don't know, Pantene and L'Oreal and what else, Head and Shoulders and things like that, sulfonic acid is what you have. Okay. So like try and read ingredients from like really common stuff as much as you can, because you'll find like some somewhat familiar compounds. It'll make organic chemistry more fun. You put context to it, like why are we studying about this? A lot of your household stuff are made of these things. Anyway, back to it. Sulfonation, like substitution is this thing. It's substituted by SO3H group. So this is generally given, like sulfonation is more effective or more common when you have greater than 6 carbon atoms, like longer chain carbon atoms. Let me write it properly. Given by alkanes C6 and above. Okay. If at all you end up having lower carbon atoms, lower number of carbon atoms, less than C6, then also tertiary carbon atoms in the lower ones will do. Okay. So these are like some notes about sulfonation. So if you want to effectively properly do this reaction, you gotta have more than 6 carbon atoms. If at all you want to do this reaction with a lower number, then tertiary carbon atoms will do, because again, rate of reaction is better in tertiary. Like general substitution में tertiary is better than secondary compared to primary. So smaller alkanes with secondary and primary carbons, it'll not react that much. You won't observe it here. All right, now coming to the actual reaction, if you want to introduce SO3H, halogenation mein you took halogen. SO3H ke liye, what reagent will you use? You don't have to give me the exact thing, give me an idea of what direction you're thinking.
Could you repeat your question?
So, substitution of alkane, obviously you need to take alkane. What should your reagent be? Plus, what should I take here so that I get RSO3H? So that I get a sulfur. So what should I take here? What reagent should I use?
Wouldn't we use halogen?
H2SO4.
There you go. So Rishit, to answer your question, agar haloalkane chahiye, if you want to substitute a halogen, we straight up used a halogen. Similarly, if we want to get this particular group, kahan se aayega? So little modification, H2SO4 is right, but we don't use acid as it is. We use a really concentrated form of it. So it's H2SO4 plus SO3 at temperature. We also heat it, 675 Kelvin. So this particular mixture, so H2SO4 concentrated with a lot of like sulfur trioxide. So this particular mixture is called fuming oleum. So oleum itself is concentrated sulfuric acid. So because you have fumes of sulfur trioxide coming off of it, it's that concentrated, you also call it fuming oleum. So you also see it represented as H2S2O7. Yeah. So when you manufacture sulfuric acid, what you get is H2S2O7. Then the manufacturers dilute it to the required amount before distributing it to, whichever industry requires sulfuric acid. So when you manufacture sulfuric acid, you initially get this only H2S2O7, fuming oleum. So as always, we'll start off like we'll do an example of this. We'll go a little higher. This time it won't be a exact direct question. So let's say I take iso.
I'm sorry to interrupt, but what did you say? Fuming? What?
Oleum. 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 So once you're done noting this down, answer this question, okay? I'll just write it first. Okay. So the question here is, where is SO3H substituted? Okay, so your answer, you need to tell me whether it's substituted on 1, 2, 3, carbon 3, carbon 4, carbon 5, or carbon 6. Like which carbon atom is this SO3H going to be substituted in the final product? Okay. So finish noting this down and then answer this question. Ritu has already answered it. Yes, that is correct.
Ma'am, could you repeat what you just said?
Rishit, have you noted it down till here?
Yes.
Okay. So I've given an equation. So I have an alkane and I'm doing sulfonation. This is the sulfonation process, making it react with H2SO4 and at 675 Kelvin and all. And then obviously I get a product. So abhi humne सीखा है कि substitution of SO3H is going to take place. So my question is, product kya hoga? Like one of the hydrogens will be substituted with SO3H. So where is it going to be substituted? Will it be on carbon atom 1, 2, 3, 4, 5, or 6? So which carbon atom will you find SO3H substituted in this case? So send the answer over chat. Abhi tak Ritu and Rishit have sent. Yes, Rishit, you're absolutely right. You got it. So if you're giving it a try, that's good. Like, give me the answer. But if you are absolutely blanking out or something, let me know and we'll do it together. Okay. Don't take a random guess. Like, if you don't know, say it. Otherwise, if you're applying any logic, like use logic and then give me the answer.
Ma'am, I'm not sure how to do it.
Okay. Sanat and Arnav and Adit, where are you guys at? You working it out or?
Sure.
What's that? It's not clear.
Not sure.
Okay. So substitution matlab any hydrogen can be substituted, right? What is the order of reactivity between the different types of carbon atom that we learned? Like यहाँ पे you have tertiary, secondary, and primary. So the rate of substitution, like which would be most preferred amongst these three?
Tertiary.
Right? So is compound में, do you have a tertiary carbon? Do you have a tertiary carbon जहाँ पे substitute हो सकता है?
The second carbon.
There you go. So the preferred substitution will happen on carbon number 2. So your final product is going to look like this. You have CH3, C, you have SO3H, and the rest of it will pretty much be the same. Yeah. So when you're asked questions on chemical properties and reactions and all, this is the direction that you need to think in. Yeah. So like that's why the order of reactivities, the preference, the stability order, all of that is important because this is how it matters. So tertiary carbon is more stable, whether it's a free radical or as a carbocation. So whenever you have, this sort of a substitution taking place, the compound will prefer like this will be the most reactive site. So whatever substitution needs to take place will happen over here. Yeah. So similarly, if we go one step, like smaller thing, like I've given hexane ka isomer because this reaction usually you find it in C6 and above. But if I were to do it in propane, so between carbon atom 1, 2, and 3, where will the substitution most likely take place? Yeah.
On the second one.
There you go. So here the only option you have is either the primary carbons or the secondary carbon. So between these secondary, like carbocation most stable, that will be the more reactive place. This is where your substitution. Yeah. So that's the kind of, like these are the kind of questions. Question is pretty direct, simple, straightforward. Reaction hai, product kya hai? Concept also is a direct thing. Sulfonation ho raha hai, to SO3 substitute hona hai. The trick to it, like this is half of why organic chemistry has that reputation. So there's one more level of thought you need to apply. Ki, okay, lots of possibilities, but kaise hoga? Yeah. Rishit's asking, we usually use tertiary because it will replace it faster, right? Correct. So tertiary is like the preferred site of it, it's a reactive site. Yeah. So sulfonation, and finally you have nitration. Okay, sulfonation. So sulfonation, substitution happening by SO3H. So nitration किससे होगा?
HNO3.
HNO3 is the acid, but what group is introduced or substituting the hydrogen?
Nitrise or nitro compounds.
Nitro is correct. Nitride, it's not just nitrogen. So it is substituted by NO2. So this is the nitro group. So NO2 agar hai, matlab you literally like naam mein bhi you get the prefix of nitro, like nitrobenzene, that way. This also, just like sulfonation, this is given by higher alkanes only. So, and reagent is going to be concentrated nitric acid. So sulfonation ke liye sulfuric acid, fuming oleum, sulfuric acid plus SO3 and all. Nitration ke liye you have concentrated nitric acid.
Ma'am, could you go back once?
Yeah.
All right, done.
For example, if we look at C6H13, It's pretty simple. Again, like it will be substituted somewhere in the middle. Generally, you get 6, 13. We start off with a hexane. Gonna get nitrohexane. Simple. Substitution by NO2, reagent used is HNO3. Same principle as that of sulfonation, just that the group and the reagent that we use changes. So halogenation, you have free radical substitution. All of these others, not exactly free radical substitution, but these are other substitutions that you do with alkanes. So after this, we'll do combustion and we'll stop there. Like remaining properties, I'll do it tomorrow. Combustion is pretty easy. 10 minutes, maybe we'll finish it off. Combustion is something that you guys are familiar with also. What do you mean by combustion?
Burning something.
There you go. Burning. Chemically, burning में क्या हो रहा है?
Oxygen is burning, right, in the combustion?
No, the alkane is burning.
It's heated in presence of oxygen.
Yes.
Oh yeah, right.
So two main points. So burning matlab it's basically reaction with oxygen. It's not just reaction with oxygen. O2 gas के साथ react करके lot of heat and light should be produced. So that's the definition of burning. So any substance, if you see that one, it's reacting with oxygen, and two, heat, light are produced, then we call it burning. If it is just reaction with oxygen, अगर ये part नहीं होता है ना, then it's not burning, it's just some oxidation reaction. But this is an important component. ये भी होना चाहिए, ये भी होना चाहिए. There's a general reaction. Alkanes general formula CnH2n plus 2 reacts with O2. What are the products being formed?
H2O and CO2.
There you go. Complete combustion matlab both carbon and hydrogen are oxidized, so you get CO2 plus H2O. The key part, like when it comes to combustion of alkanes, everything is intuitive. And of course, you have plus heat and light. The key part is balancing the equation, which again is pretty easy to do. अगर n carbon atoms है, तो कितने CO2 will be produced?
N.
N
CO2. And 2n plus 2 hydrogen है, तो how many water molecules will be produced?
N plus 1.
N plus 1.
And just one.
Yeah. So you can write this as 2 into n plus 1. हर एक water molecule में 2 hydrogen है, मतलब divided by 2 n plus 1. So once you have number of carbon dioxide, number of hydrogen, water, you can easily get the number of oxygen molecules from this. So यहाँ पे NCO2 है, have a total of 2n oxygen, n into 2, and n plus 1 oxygen in water, n plus 1 into 1. यहाँ पे O2 है, मतलब you just add both of these, so you get 3n plus 1 by 2. So if you're very good at memorizing, you can just memorize 3n plus like these values, and then you can balance any alkane combustion reaction in the universe. Or you can use the same logic to figure out again the balancing for any combustion reaction that you're given. Yeah. There's nothing else to combustion. It's literally burning. When you burn any carbon compound, you get carbon dioxide. If it has hydrogen in it, you get water vapor. That's it. So alkanes, again, special note, they burn with blue flame. Which is why alkanes are like major component in any sort of fuel that you use. Petrol, diesel, may you have like unsaturated hydrocarbons also. It's a mixture of things, but mainly you tend to use alkanes. Like now we are moving towards cleaner fuels, so you end up using CNG, compressed natural gas. Abhi LPG cylinders or pipes, what you use for cooking is also all alkanes, mainly natural gas, but sometimes mixed with some butane also. Welding, maybe when you use that, like if you guys have seen things being welded, a lot of heat is required, you have that flame coming in, right? So you have a type of welding called oxyacetylene welding. So it comes from the fact that you use acetylene. Okay, welding may you use ethyne or an alkane.
I think I did not hear it properly, but did you say if only carbon and oxygen is there, then we'll only get CO2, right?
Yeah. But hydrocarbons,
Just-
alkanes are hydrocarbons. You get CO2 and H2.
Yeah, I wanted to clear that.
Yeah. So cooking, like half of, like who all are into cars and bikes and things like that. High speed, Arnav, okay. So you must come across all these words like high octane races and, again, there's
Yes, a bit.
yeah, octane is a fuel used. Octane is it's an alkane. That's where you get a lot of these terminology from. Alkanes, that's like the primary main use. So one part of it is to produce other other organic compounds, alcohol and all that. But even more than that, they're used as fuels. Cooking ke liye, like fuels when you're going places. Fuels even when you need heating in industries and things like that. Very good, very efficient, very clean fuels. Okay. So another side of it, like if you allow alkanes to burn in air, they're gonna take how much ever oxygen is required. They're going to use this whole 3n+1 of it. So there's another side of it. If you end up controlling the amount of oxygen, if you are providing the oxygen in a closed vessel, closed place, then you end up having incomplete combustion. So when it's not a complete combustion, so incomplete combustion happens when you have like insufficient oxygen. Then in this case, water, like hydrogen is the only one that's oxidized, and you end up getting carbon black. So carbon black is your soot, charcoal, like black substance, plain old carbon. So I know Ritu and Smira do art. Others also do art, like you have charcoal pencils, right? That's basically it's carbon, pure carbon. Yeah, balanced. instead of the required amount of oxygen, you limit it, then you end up getting. Which is why, like, a defining factor of incomplete combustion is the flame is dirty. It's not blue, it's yellow, orange in color. And you also, because of the carbon particles, some amount of the carbon is going unoxidized. The flame that comes out of it is also like dark, because black flame basically has like little carbon particles. And that carbon is not converted to carbon dioxide because there is not enough oxygen. So basically, there's incomplete combustion. Yeah. So that's about it. After this, we will be talking about oxidation. So this is like free range oxidation. You're using air to oxidize it. We have controlled oxidation, meaning you are controlling the oxidation. We're doing it in lab. That's another important reaction. And apart from that, we have just 2, 3, 4 more reactions. They're like pretty tiny. Isomerization. How do you create benzene? Aromatization. And pyrolysis. Cracking. Like cracking of petroleum. Yeah. So after this, there's only like one major reaction when it comes to alkanes, and then we can start off with alkanes. Okay. Any questions? Anything else you want to discuss?
Ma'am, so I wanted to know, how is it insufficient? Isn't O2 enough?
So that's what I mentioned. If you're controlling how much oxygen you're giving, so if when you're burning a candle flame and all, like oxygen is there in air, so it'll take how much ever is required. But if you're doing it, let's say in a reaction vessel, or if you're doing it in a closed vessel, like a closed stove or something like that, where the amount of air or amount of oxygen is being cut off, or maybe, like let's say this is your vessel, you're passing your alkane through it, and then there's just a tiny opening for air to get through. There's not enough oxygen being available because it's all like completely closed and stuff. You're just pumping it full of the alkane, but not enough oxygen is there. Then your product, like more methane, less oxygen. Like, let me compare it. Suppose in incomplete combustion, methane and oxygen are in 1:1 ratio. If you want complete combustion, let's see what the ratio is. Single carbon, okay. This will be 2. 2 plus 2, 4. This will be 2. So 1:2. So if you're sending 1 liter of methane, 1 liter of oxygen, like when you're doing it in a closed vessel condition where you are controlling how much of each gas gets to go, then you can end up with incomplete combustion. If you're letting it happen in like open air, like let's say this is the pipe and flame is over here, it can take how much ever oxygen it wants from the surroundings. So then you get complete combustion. Okay. Does that answer your question, Rishit? Make sense?
Yes, ma'am. So basically, if it is controlled, even though O2 is being given, that would be insufficient, right?
Yeah.
Okay.
Right. Should I end the session? Is there anything else you want to discuss? Any doubts? Anything?
I guess that's it, ma'am.
Yeah. Are you done noting things down?